Hey, welcome back. So one of the things I've realized is a lot of people struggling with what's happening underneath the hood with Rust. It all feels a little bit magical to them. Now, I don't believe in magic. This ain't Harry Potter. So what we're going to do is we're going to break down Rust and we're going to convert it into assembly language. Now that probably sounds quite difficult, but actually I'm going to walk you through it. It's going to be super simple. And at the end of this, you'll be able to actually convert your own code into assembly language. And it's really going to help you deepen that understanding. Because if you understand how variables work and how you understand how mutations are working and how it is represented in assembly, then it's going to be much easier for you to get some of these larger concepts such as ownership and borrowing, etc. Because you're going to understand exactly what's happening underneath the hood, and you're going to understand what the difference between a stack and a heap is and how that's represented in code. So with that being said, let's write some Rust code and then let's look at how that looks like in assembly. Okay, so the first thing we're going to do is create a new Rust project. I'm going to do that with cargo by just typing in cargo new Rust assembly play. So we'll just do that, and then that's going to scaffold up our code. And then, as you can see, it's created a directory, and my code is there. So if I type in code dot, then it's going to open up this new scaffolded project in Visual Studio Code. And now what I'm going to do is I'm very quickly going to write a brand new function, which is just going to do something a little complicated. It's going to do some multiplications and some additions, etc., assigned to some variables, and then what we'll do is convert that into assembly. Alrighty, so the first thing we're going to do is initialize some variables. So I'm going to have two variables, one called num1, and I'll set that equal to 10, and another variable called num2, which I'm going to set to 20. Then what I'm going to do is multiply the two numbers together. So we will set result 1 equals num1 multiplied by num2. Then what I'm going to do is I'm going to do another calculation. So, and this time I am going to take num1 multiplied by num2, and then I'm going to multiply that by 2 again. So I'll put num1 times num2 multiplied by 2. And then the last thing I'm going to do is do result 3, and that is going to be equal to result 1 plus result 2. For all of you trying to do the math at the moment, the math is not that important. What I'm trying to do is just have some multiplications and some additions so that when we look at the assembly language, we can see some of the optimizations that are occurring underneath the hood. So last thing we're going to do is going to print out result 3. So we will just do println result 3. That will do. I'll add a little message of the value of result 3 is whatever the answer is. So that's our very super simple Rust program. What I'm going to do now is switch back to the console. We'll just clear this, and then if we do a cargo run, we should get an answer. And as you can see, the value of result 3 is 600. And that makes sense because what we're essentially doing is 10 multiplied by 20, which is result 1, so that's going to be 200. Then what we're doing is num1 multiplied by num2 multiplied by 2, so that 200 is going to then be multiplied by 2, which is 400. And therefore, what we're now doing is taking result 1 plus result 2, so result 1 is 200 plus the result 2, which is 400, which is equal to 600. So well done, Rust, you are a good mathematician. So how do I emit assembly? Okay, so if we look under the your target debug folder here for a second, one of the things you notice is you see the Rust assembly play, which is the executable that we generated. In fact, if I were to open that up in my console for a second, so let me just open up a new tab, and then if we go into target, and then we go into debug, and then if I were to run Rust assembly play, you can see it executes the code. Now, if I come back in here, what you're going to see is lots of output files, etc. So what Rust is actually doing underneath the hood is it's going through a build process, it's creating all these various object files, etc. And then what it's going to eventually do is take that and then convert it into the executable. What I want to do in this case is part of that build process, I want it to actually emit the underlying assembly so I can take a look at that. Now, how I do that is if I come back here, and then what I'm going to do is just type in Rust flags equals, and then I'm going to do -- emit ASM. So it's basically saying I'm setting a Rust flag and I'm going to want it to do emit ASM. So go generate me some assembly for the code that I've written. And then if I just do a cargo build. So now that it's done that, if I come back into Visual Studio Code for a second, and then we come back into that deps folder for a second, what you're going to notice now is generated a .s file. And if you have a look here, we'll just ignore this for a second. You can see it's generated a load of assembly. And then if I were to scroll down or even just do a search for main, you can then start to see some of the code that's been written. Now, in this particular case, this is written in ARM because if you think about this for a second, I'm running this on an Apple Silicon M1. So I don't really want us to look at ARM assembly. I want to be looking at more of the Intel-based assembly because that's what most people are going to be running on their machines. It's also a little bit simpler for us all to understand as well and a little bit more standard. So what I'm going to do now is I'm going to cross-compile this into Intel for my Mac, and then therefore it's going to be more like what everybody else is going to be able to see. To do that, let me just clear this. The first thing that I need to do on my machine is I need to be able to set the target so that I can target x86 rather than ARM64. So I'm just going to type in rust up target install x86 64, and we'll put Apple and Darwin. If you're not sure what targets you have on your machine, you can just type in actually rust up target list, and then that's going to give you a list of all of the targets on the machine. So you can kind of see there's things like WebAssembly WASI, there's WebAssembly unknown. So because of course Rust, and then you can see there's Arch64 Apple Darwin, which is what it was generating earlier. So if you're unsure which target that you've got, you can just type in rust up target list, and then you will see what type of targets are kind of available. And that's actually super important because Rust can obviously compile to multiple build targets. It can compile to WebAssembly, it can compile to Intel, it can compile to ARM. So, you know, the assembly that it will emit would be different, etc., for what you're building for. Now, so in this case, we're going to be building for an Intel machine, so I'm going to cross-compile to that. So let me just clear that. And what we will now do is I'm going to do a cargo build -- target. And now I'm going to use that target that we saw from the rust up target list. So I am just going to type in x86 underscore 64 Apple -Darwin. And now it's going to compile that for the Intel-based machine for an x86. So again, if I want to run it, I can do a cargo run -- target x86 underscore 64 Apple -Darwin, and then it will run, and then it says the value of result 3 is 600, so it still works. And that's because underneath the hood, even though I'm running an ARM64 machine, it's an Apple Silicon M1, because of the magic of Apple and Rosetta, etc., it's able to run x86 code anyway. So that's all kind of good from my machine. But more importantly now is that when I emit my assembly, then what I'm going to be able to do is look at Intel-based code. So let's just clear that. And then what we're going to do now is we're going to run that rust flags emit ASM cargo build, and we're going to have a look at the assembly. Alrighty, so now that I've compiled that, if I go back to that deps folder, you can see there's a Rust assembly play there as well. And if I do a search for Rust assembly play, you can see there's kind of multiple entries there, but now it sort of brings me back down and I'm roughly at my kind of main function. So one of the problems with the S files that you've seen there, it's actually pretty hard to read. There's a lot of gubbins within there. So what you really want to be able to do is have a look at something that just makes it a bit easier to read. So I'm going to use a tool called cargo show ASM. So I'll just do cargo install cargo show ASM, and then that'll take a second to get that installed. Once that's installed, what I'm able to then do is run a piece of code that will make it a little bit easier to read. So I can do cargo ASM rust assembly play, And then one of the things I can put in is the name of the function that I want to display. In this case, I know it's called Rust_assembly play colon main. I'll show you in a second how you can find out those answers. So I want the dev build. So I want that to give me a debug file, hence why I'm using --dev. I need to put in my target again. So in this case is x86 64-apple Darwin. And then the last thing I want to do is say interleave my Rust code with the assembly so I can look at that. So if I run that there for a second, you can now see it's sort of come back and it's a little bit easier to read now, right? So I've got my my code here. There's my fn main, and then it's showing you some of the assembly code. And then as you are going through each line of code, you can see my let num equals 10, and then the associated assembly that goes with that. So that makes it a little bit sort of easier to read. But don't worry, this is probably still looking quite scary, but we'll break it down a little bit further. If you don't know what the name of your function is, you can just type in cargo ASM and hit return. And then it's going to give you some options. So you can see there's a whole bunch of sort of generated functions that we don't care about. But there we go, Rust assembly play, colon main. However, even then, it's probably still a little bit complicated, but here's an even simpler way of doing this. So I'm just going to open up Brave, and then I'm going to go to a tool called godbolt.org. And then what I can do here is this is a sort of a compiler which will generate the assembly for loads of different languages. I just need to select Rust here. And then you can also see that you can pick the various compilers that you want to run. So I'll stick with Rust 163. And then I just need to paste my code in here. So if I take my main RS that I've got here and then just copy this, and then just copy this into Compiler Explorer. To make the main function work with Compiler Explorer, I just need to set it to being public for a second. Once that's done, it'll work. And one of the nice things about Compiler Explorer is it's actually very nicely generated. So it's quite easy to read and understand the code. So rather than necessarily messing around with Cargo ASM, you could just go into this for simple lines of code for you to understand what's going on underneath the hood. And I think it's a little bit simpler, so I would recommend that you use godbolt.org. It's probably the easiest way of doing that. So the first thing that I want you to see at the moment is you can see there's a nice little label there, which is example main. So what I've got is my function called main here, and you can kind of see that it's represented here. So there's my function. Now this first line is called sub, and then RSP, usually that is referring to the stack pointer. So if you think about functions for a second, functions are held on a stack. And as I call through my functions and then I call other functions, then essentially I'm sort of working through this stack. Now I'm not going to go through this in too much detail. Stack is very fast kind of memory, but essentially just think of function. And within the stack, and if you don't know what a stack is, it's like a kind of it's like a stack of papers, right? So if I want to add something to the stack, then I push onto the stack. So I might push an item and then push another item and push another item and push an item, and I have a stack of papers. And then when I want to take something off the stack, I just pop it off, pop. So that's really what's going on underneath here. But essentially every function's allocated a stack frame, and therefore every variable that exists is sort of constrained to that. So really what is happening when you see this sub RSP 104, there's a starting point of the stack and it's saying subtract 104 bytes from that. So basically it's saying allocate me 104 bytes for the example main function, right? That's really what's going on here. So it's a sort of fixed size of a stack frame. So it's just saying everything I need to do is going to happen within this 104 bytes. So the next thing that's happening here is you see this MOV, EAX, and then 10. So essentially, if we come back to here, you see let num1 equals 10. So the next thing that's happening, I want you to see here, is you see this EAX, MOV, so that stands for move or copy. So, and what essentially happens is two arguments. First argument in this case is a register, and the second argument is a value. So really what it's saying is copy the number 10 into a register called EAX. And you can kind of see at the moment there's a sort of one-to-one between variables and registers. It's a little bit more complicated than that because they're going to get reused, but essentially that's what you're seeing in this particular case. So let num1 equals 10. So in this case, it's take the value 10 and stick it into the register EAX. The second thing that you've got here is I've got let num2 equals 20. So in this case, it's saying take the number 20 and then stick it into the variable ECX. As it stands, I've got a variable called EAX. So the first move statement, EAX, is now going to have the value 10, and then the second one, ECX, is going to have the value 20. If I come back to my code for a second, the next thing that I'm going to do is I'm going to take variable num1 and variable num2. I'm going to multiply them together, and then I'm going to stick the result in a new variable called result1. So let's see what's actually happening underneath the hood here. So you can see there is a nice little assembly operator here, which is imul. And what's that saying is essentially you're going to be doing a signed multiplication of two operands. So that's fine. So, and it's going to take ECX and it's going to multiply it by EAX. Now, the key thing that I want you to understand is EAX is the starting position. ECX, which is 20 at the moment, is going to multiply by whatever is in EAX, which is 10. And then the result is going to be stored in EAX. So what will now happen is EAX will no longer have the value 10. It's going to have the value 200 because it's taken the 10 and the 20, multiplied them together, and then it stored it in EAX. Now, the reason it can do that is there is nothing else accessing the register EAX. Now, you might be thinking to yourself, hang on a second, there's a calculation here which is num1 multiplied by num2. So you might be thinking to yourself, hang on, surely it's got to access EAX again because I'm going to take that value num1. We'll come on to that in a second, but the answer is essentially no. It doesn't need that value because the compiler is going to do some optimizations, which I'm going to show you in a second. So the next thing that happens is it's going to take the value EAX. So EAX at this point is going to have the value 200. And then what it's going to do is going to do a move, which is a copy, and it's going to take that EAX value of 200 and it's going to put it in essentially a memory location in the stack frame. So if we look at this, you can see RSP plus 32. So there's a pointer to, this is our stack pointer. Remember RSP over here. So if we just add 32 bytes onto there, so 32 bytes onto where the stack pointer starts, then essentially from there, the value 200 is going to be stored there. Now that is a good thing to be aware of because essentially in advance, fixed calculation sizes of storage of local variables is going to be calculated and be able to store within that stack space. So it's all calculated up front, right? So that calculation, result 1, which is num1 multiplied by num2, because we know that's a 32-bit integer, that can be stored in there, and there's a fixed allocation size that's going to occur. So there we go. So if we come back to the slide for a second, what you are going to see here in my stack, 32 bytes from the stack pointer, you're going to see the value 200 sitting at the top there. So it's just sort of popped on there. Now, the next thing that's happened is you've got this seto thing. So what is seto? So, and it's doing it on the register A1. So what seto is doing is actually testing for an overflow. So if I have two integers multiplying together or whatever, and then it goes bigger than the greatest size of the integer. So let's say, in this case, it's an I32. So if I have a very large number, then essentially you get into this overflow scenario. So what Rust is doing here is putting a little bit of assembly code in here that says, go check to see if an overflow just occurred. And if an overflow did occur, then stick the result of the overflow in A1. So once that's done, it's going to do a test for the overflow, and then if an overflow does happen, it's going to jump down to label _2, so LBB3_2, and then essentially what it's going to do is panic, and you're going to get an exception of some sort. If everything is fine, if there's no overflow, it's going to continue on here. So the next thing that's going to happen is we're going to take the value, whatever is in dword pointer, 32 bytes from the start of the stack pointer, and it's going to load that in to register EAX. Now, if you remember, EAX has got the value 200 stored in there, right? So it's got the value 200 over here. So what's actually happening in this case? Well, actually, this is kind of smart enough to realize that num1 multiplied by num2 is a calculation that's already been done, and it was stored in result 1. So the compiler's kind of worked that out, and that's something to be aware of, is the compiler can do some basic calculations, so things like additions, etc., or have a look at where there's some duplication, and then be able to do some reuse. So now as it stands, in EAX, we're going to have the value 200. Now, the next thing that it's going to do is with the register ECX, we're going to put the value 2 in there. Again, if we come back to the slides for a second, what you can see here is EAX has got the value 200 and ECX has got the value 2. So what's going to happen now is we're going to do another imul, and if we remember that from before, then it's going to take whatever is in the second operand, which in this case is 2, and it's going to multiply it by the first argument, which is EAX. Great, so it's going to be 2 multiplied by the 200, and that's going to be equal to 400, and that's going to be stored in EAX. So EAX is now going to be have the value 400. And then what's going to happen is it's going to store the value 400 in RSP plus 28. So I want you to come back to that stack for a second, right? So result 1 has got the value 200 in there. But then if we go slightly higher, so just one up on the stack there, what you're going to see is the value 400 is there. And you can see that it's 4 bytes apart from the 200. And that's because of the sizes of the integer. These are fixed sizes. So if I change that from being an I32, for example, and I put some other value in there, maybe it was a float or something, or it was a Boolean, then that's going to have a different sizing. So this is all of the sizing. This is where it's using your types and the size of your variables to calculate the amount of memory that it needs within the stack and how it is able to be super fast. So anyway, we've now got 400 stored in that location. And again, if I come back to my keynote, you can kind of see that here. Now I've got 200 at RSP plus 32, and then I've got 400 at RSP 28. So it's using that allocation of memory on the stack to go along. So the next thing that is then happening is it's doing that kind of seto piece again, and then it's also doing another test. So it's basically checking for an overflow once again. And if an overflow happens, it's going to jump down into label 4, which is going to panic again. But if underneath the hood, everything is fine, it's going to jump to label 3, right? So, by the way, just so everybody, let's be utterly clear here, these label jumps, these are goto statements, right? So, for everybody that goes, oh yeah, gotos are terrible, and they are in the higher level programming languages, but actually underneath the hood, that's how assembly works. So if we look at this line of code here for a second, what we're going to do here is we're going to take result 1, which we know is 200, and we're going to add it to result 2, which we know is going to be 400, and then we're going to store it in result 3, which will give us 600. So let's look at the underlying code there for a second. So the first thing I can see is I've got a move statement, which we know is a copy, and it's going to take the value from dword pointer RSP plus 28. So it's going to go to the memory location in the stack of plus 28 from the stack pointer. So we know that that was 400. And in fact, we can come back to our slides there. There's RSP 400, RSP plus 28, which has got the value 400, plus 32 has got 200. So what we're going to do is we're going to take that value and we're going to put that in EAX. So EAX, the register, is now going to have 400. The next thing that's going to happen is we're going to take the value 200 and we're going to add this to EAX. Why is it not just actually pulling in from dword RSP plus 32? And that's because the compiler is smart enough as it's gone along, right? It knows that the value is 200 in this particular case. So it's done a little bit of compiler optimization and it's just shoved 200 in there, and then it's done the addition. So this is one of the things to kind of be aware of, right? Especially for addition functions, if it can do some simple calculations and a compiler can work this out in advance, then it will do that. Now remember, these values here are all immutable in Rust, so there's no chance that they're going to get changed or anything underneath the hood, and a compiler has done all the calculations. So it's pretty good, and it's just doing that. So EAX, if you think about it, what's going to happen here, and the add command is very similar to the mul. So what it's going to do is it's going to take the value 200 and then it's going to add it to whatever is in EAX. So remember, this is an add, not a move. So if it was a move, EAX would have 200, but because EAX has got 400 in there already, it's going to take the 200, add it onto the 400, and then put the result in EAX, which is going to be 600. And then of course, the next command here that you're going to see there is it's going to take that 600, which is in EAX, and then it's going to put it to RSP plus 24, so the stack pointer plus 24 bytes, because essentially we're dealing with 4 bytes here. So that is now copied in here, and the value 600 will be at RSP plus 24. So we come back to the code for a second. What you're now going to see is EAX obviously has the value 600, and now 600 is stored at RSP plus 32. So I've got 200, I've got 400, and now I've got 600 at RSP plus 24. So now that it's done that calculation, it's obviously going to do some further tests, again, for overflows, etc. And then it's either going to jump to number 6 if there's an overflow, so label 6, and it'll just panic. And if it hasn't panicked, then what it's going to do is get down here, and then essentially it's going to set itself up to do the final print line. The value of the result is blah blah. So I'm not going to run through this piece here because it's going to eventually land at label 7. It's going to run through all of this, and then you can see sort of standard IO sudo print macro, and that's then going to call the standard function, which is going to print out the value of the result is blah blah. So that's kind of how that works.